All right, let's jump back into everything now. And we're going, so in the prior step, we have generated a time series of residual greenness for our focal area. And that is going to be our data set that we are going to input into to a time series segmentation algorithm for us to try to gather some parameters to describe how every single pixel is changing over time. And the algorithm, the approach we're going to be using is called LandTrendr, and it was developed by Robert Kennedy and his team at Oregon State. And this is a great figure, I think, that they have developed to kind of explain what we can get out of their approach. I point you to some of their technical papers for the nitty-gritty about what is going on behind the scenes in terms of how they identify some of these and how they're breaking apart the time series. But I'm just going to focus here on what we are the utility for us in this particular process. I also want to point to the really great resources that he and his group and Justin Brayton have put together for to kind of illustrating the integration of LandTrendr into Google Earth Engine and some of the various things you can do with it. And there's some good UI interfaces in here as well. So I highly recommend all of the great work that they've done on that. So we're going to be applying this LandTrendr algorithm to our time series of residual greenness. And from this, we will be able to derive a lot of information, not all of which we're going to be talking about today, but essentially for our time series, it's going to kind of fit a line or a series of segments and give us information about what is the start value and end value of every segment in that time series. What is the year of each vertex when the time series starts to change, and what is the magnitude of change between each vertex? Right? How much has it changed between from year 1 to year 2, or the start year and the end year of a particular segment, and what is the duration of change along that segment? It really helps us to break that apart. There's really a lot of information. We're going to be focusing today on the information about what years a particular time series is changing, what are the vertex years, and what are the values of these vertices in those given years. But we can pull out a lot of other information as well. Oops, get out of here and just go to my next checkpoint to walk you through that. And we're going to be starting at about line 108 in here for this next checkpoint. And the first thing we need to do for the LandTrendr algorithm, the way that it's implemented in Earth Engine, is define a number of parameters. And I won't go into all of these because you can read some of their resources and references in terms of what these are capturing. But if you do that, you'll note that our parameter settings are slightly different than their recommended ones for forested systems. And that's because we're trying to detect typically more gradual changes. We're going to be more sensitive to more gradual changes. So we're going to load that algorithm and run it with our specified run parameters, and using our we have also added in our residual greenness collection into that. And then we can select out some output parameters from that. And let me just run this here so that you can see. And what we get from LandTrendr is bunch of arrays that require a lot of slicing, and there are some, I think, resources about slicing arrays in the book, but it does take a little bit of time to wrap your head around it, so I'm not going to get into it too much today. But I've put the code in here for slicing out the years and the fitted values and how we kind of pull out the various pieces of data that we want to use. And the next parameters that we need to define are what years we're going to be looking at within this particular set of time series. What is the range of years that we have? And we're going to, there's some code in here for you to extract the residual value, the fitted residual that we get out of LandTrendr for every single year, and aggregate that into a new image where we have one band for each year. So we end up with a time series that is nested within a series of bands within a single image. It's the first way that we can start to pull that together. And we are going to add that to our band, or to our map. We're calling this our fitted stack. It's our stack of bands of the fitted values. And then we can visualize particular bands, a single band at a time, to start to see what are the residual values that are predicted or sort of fitted from the LandTrendr output. And we can compare those to our observed values as well. Start to see how those kind of correspond. And then the next thing we're going to do, so we've got to is take that, and then we're going to essentially put together a new set of data that for every single pixel asks, is there a vertex in this year for this pixel, and creates essentially a Boolean time series for each pixel, right? A set of ones and zeros that indicates whether that pixel had a vertex in that given year. I'm going to actually illustrate this back on my slides. I think it'll be a little bit easier to show you this way. So these are, again, what we just saw on the other screen. This is our fitted values from LandTrendr for residual greenness. And this is, right, we're just pulling out this year, 1980. This is where we're headed next, is to get out a Boolean value for each of these years. So this was the image with multiple bands of residual greenness per year, and we're going to work towards getting a image that has Boolean values for each year in terms of whether it has a vertex. Whoops, excuse me. And actually, I'm going to scoop ahead on this and show you essentially what that might look like, right? So here's for a particular year. And this is the visualization of those ones and zeros, right? So our zeros are coded white in this image, and the ones are coded red. So in 1997, all the pixels that are red in this image had a vertex in that year. And we can start to see that there is some clustering, right? It's not completely random across this image. We start to see areas, geographic areas, where there seems to be some clustering of change. So it kind of suggests there might be something, right? There's some there's something going on that might be triggering some of that. And then the other thing that we can look at from this is we can pull out the mean number of Boolean values for the entire image for a particular year. So we were just looking at 1997, 987, right? So that was a big year of change, right? Almost 20% of the image had a vertex of the ROI had a vertex in that particular year. And so for each year, if we gather, right, that number, we can start to see there are certain years that have more change than other years. There are some signal in there that there's years where there's more change happening, or the beginning of change that's starting to happen in those particular years. And that gives us something to think about at the end, when I'll come back to this, in terms of thinking about what are the drivers of these changes. So let me just run you through. See. So this is plotting the individual years and charting. So here's our chart code for charting our Boolean mean per year. And then we can choose individual years, right, that we might want to view. Again, I've got 1997 queued up here, but we could look across different years to see, perhaps we might want to look at 1990 instead, right, to see, okay, well, what are the spatial patterns for 1990? And this might take a second to run. Oh, and I didn't change my annotation on here, but this is now 1990s patterns, and you can see there are fewer vertices in this year, but also the locations of those vertices are different than they were in 1997. This is now 1990. And one of the interesting things that we can do with this, with some of the other code that's available through Earth Engine and some of the other UI tools, right, is start to look at this over time in sort of a spatial temporal loop, and start to see how this is across the entire focal area. We have been looking at a specific region right in here to say, how is this, where are things changing in a given year? And are there particular years where there's certain focal areas of change and where there are more significant number of pixels that are changing in that year? Oops, should put that back on slideshow, sorry. And from that, right, we're not just interested in kind of eyeballing this. We kind of want to know, well, what is actually going on under the hood here? So again, this is our visualization of all of the pixels that had a vertex in 1997. And we can extract summary information about those pixels. So for instance, here we just have, what is the median residual greenness for all of the pixels in this that are red in this particular image, right? So this is sort of the median value. This is the sort of median trend that's going on across all of those pixels. So we see, right, we've got this vertex in 1997, and over time there had been a gradual decline, and then there was a slow, steady increase in greenness across all of these pixels, somehow associated with this change in 1997. However, we can see, right, pixels that had that change in 1990 had a much steeper drop in their residual greenness, and they began their increase in trajectory much earlier than these pixels. And then I'm just showing you another really different example of the set of pixels that changed in 2012, where there's this really slow, gradual, not much change at all over time, a little bit of an increase, and then suddenly around 2012, a rapid increase in greenness, right? So there's likely different processes, right, driving each of these different kinds of trends. And so we were interested to see, right, can we take all this information and use that rather than just our endpoints? Can we use the characteristics of these time series for classification? And so that's where we are going to go next. And this is our code checkpoint D. Let me scroll down to the start point of that. And this is a pretty short checkpoint that just outlines the pretty standard way that we fit an unsupervised classification, k-means clusterer, onto our set, just using those Boolean values. So we're not using any, actually at this point, any of the additional information that we could get from LandTrendr as far as what is the magnitude of any of those changes or the durations. We could bring in some of that information as well. For now, for this example, we're just using that set of Boolean values for each pixel of whether it had a vertex in a particular year. And based on those, we create some training data. In this particular example, we're setting it to consider up to 10 classes for this. Again, there is information in other chapters of the book that will walk you through the processes for running classifiers. So I won't get into that too much here, but just kind of wanted to show you what we were putting into the classifier. And then this is just a random visualization, so just random colors assigned to each class of the 10 classes that we got out of this unsupervised approach. And here's another kind of closer up visualization of that here. And what I wanted to point out here is that, we do see certain classes clustering in certain areas and others that are, we tend to see kind of across the image, and certain ones that we only see in certain places. So there is some spatial patterning to the clusters that we are getting out based on this time series information. And of course, there are many things we could do to further refine this in later, if we wanted to get more sophisticated with this. And so one of the things, though, that I just want to show you is that we can kind of essentially describe in the same way that we were looking at, well, what does the median greenness look like over time for all the pixels that changed just in 1997? Well, now we can add that same approach to asking, well, what's going on within a particular cluster? What does a particular cluster look like in terms of its time series? And so we essentially add the cluster number band to each image and combine that with our median green, both our median greenness observed and our fitted greenness from LandTrendr, and add those into new images so that we can start to visualize those. And that is our code checkpoint E. And this checkpoint is, what we cover in this checkpoint is essentially just exploring and looking at what's going on within these particular clusters. And so here's, so once we kind of combine the cluster number and observed and fitted greenness values all together, that we can start to ask, okay, well, what is the median observed greenness for all of the pixels that are classified in cluster 1? And what is, we can look at each different cluster to see how these trends, this is the fitted trends from LandTrendr here, how are these different across the various clusters? And rather than bring each of these up sequentially, I'll show you a couple examples back in the slides in 1 second. But I just wanted to note that the bulk of what's happening within this code chunk is combining the cluster information with our greenness values, and then some code for essentially plotting these charts over here. And so there's some sort of wordy chart plotting in here, but that's essentially what's going on within this final chunk of code. And the final thing that I wanted to do was essentially, so this is the fitted residuals for cluster here. And then the final thing I wanted to do was look at, well, what if we look at, again, back at those MODIS data that we started with, just kind of picking different pixels on this landscape, how are those changing? And so this is just picking a particular point. So you can try with different points or with a set of points, and just looking at how or whether there was any change in the MODIS classification for that particular pixel. So this is a pixel that is classified as cluster 1 in this output. And MODIS land cover 10 is the grassland classification. And we can see, according to MODIS, this particular pixel has not changed in its classification over time. But according to the to our residual greenness, right, there really has been both a decline and then a slow and steady increase in greenness over time, right? There is something going on. It's not just a static grassland class there. There's something going on that we don't capture just from the MODIS data. So I just wanted to show you an example of a couple of those side by side, so I think it makes the point a little bit more strongly. So here's again cluster 1 that we were just looking at, and here's a spatial pattern of pixels that we that are classified as cluster 1 in this particular data set. Here's an example of cluster 3 and how that has changed over time. And we see those are largely clustered in the northwestern portion of the range, and a little bit more flat over time in a slightly later time when it started to gradually increase. And then here's cluster 4, which is spread out much more across the entire study area and has a much more abrupt change in the direction of the trajectory around 1997 again. So this is essentially a lot of what's going on in that 1997 data set is captured within cluster 4. Gradual decline and then abrupt change into a positive slope rather than this kind of more gradual flexible change over time. Oops. And so just to, in summary then, so this is telling us, right, that there are, there's like clubs in our data, right? There's certain kinds of trajectories, right, that are more similar to each other than other trajectories, and those tend to have these spatial patterns as well, these kind of distinct spatial patterns. We have spatial patterns of our temporal patterns. Which is telling us a lot more, right, about when we have, instead of just having this be classified as grassland, we know that within this particular cluster, it has been changing in this particular, these pixels have been changing in this particular way, and that might inform how we would anticipate that this pixel might change in the future. Now, the big next step in all of this that we're still working on, right, and that I think is the next big phase in thinking about this is the why, right? What are these pixels responding to? And in order to, so can we start to attribute some of these trends to particular management practices, particular policies that were implemented at particular times, particular climate shocks that are, outside the range of the typical variability, things like that, so that we can start to understand, beyond just that they're changing in different ways, but what is actually driving that change, and does that help us to kind of explain why one particular, set of the landscape is changing in one way, and one set of another part of the landscape is changing in another way. So that's sort of the next big step that I thought I would leave you with in terms of thinking about what you could do with these. And then in addition is sort of thinking about, okay, well, if we have some knowledge of the history on the ground about what policies were put in place when, then we can go beyond just an unsupervised classification approach, but just thinking about, can we develop some training data based on particular management that was put in place in particular places, and kind of train our models and to be a little bit more informed from the get-go.